Hello. Right, let's continue onwards. Diva Design Service employs 60 people. Employees are asked to log on to their computer, but at 9 a.m. on Thursday, the number of employees logged on was recorded every 10 seconds from 9 a.m. Use a cumulative frequency diagram to estimate the median time taken by the employees to log on. Right, so the important thing to note here is that there are 60 people in this data set, so the median would be at 30. So what we do is we go to 30, and we go across like so. And again, it is important to draw your line with this. It is really, really important. So the median time was 40 seconds. Diva Design Service has a policy that states the following: 90% of employees should be logged onto their computer by 9:01 a.m. Okay, so there are 60 people in the survey, so the 90% mark would be 60 take away 6, which is 54. So 54 people. So show that this policy was met on Thursday. So we need to show that above 34 people were logged on by 1 minute past. So 9:01 would be 60 seconds after 9. So we go 60 seconds onwards. And we go across like so. Right, so every box is, it's 10. One big box is 10 little boxes, so each little box is 10. So I get this to be 3 less than 60, which is 57. So 57, so yes. So we needed 54 people, and there are 57, so yes, there are. Alan Frames is a company that employs 360 people. 6 of these people are selected to just discuss changes to the company logo. The manager has decided to use a systematic sampling method. He has numbered a list of 360 people. When using a systematic sampling method, where should the manager start this selection for the 6 people? It should be chosen randomly. This is just bookwork. Unfortunately, there's no skill to it. It is just bookwork. When you perform a systematic sample, your first instance should be random. The manager actually starts by selecting the 4th name on the list. Complete the table below and give the position of the 6 people who would be selected in the systematic sample. So there's 360 people, and he wants to select 6 people. So the way systematic sampling works is simply put, here's the 360, and I need to find 6 people. So what I do is I break this into 6 boxes, and he's taken the 4th person, which is this person here, which I'll label this, and then we need to then find 1 person in that position in each box, essentially. So each box is going to be worth 60, because it's 360 divided by 6, which is 60, and it's important you show this, because in the marketing they will be looking for this. So it's every 60 people. So the difference between this and this would be 60. So it's 64, 124, 184, 244, and then 304. Nice and straightforward, nothing too difficult there, I would hope. Okay, next one. Box plots. So David works in a call center. On Monday, he made 200 phone calls. He recorded the length of time spent on each of these phone calls. David noted that the following about the time spent on each phone call. So to draw a box plot, we need 5 things. We need the minimum, we need the lower quartile, we need the median, and we need the upper quartile, and we need the maximum. So these are the 5 things: minimum and maximum, lower and upper quartile, and the median. So the greatest time was 2 minutes and 10 seconds. And I'm noting here that the axis is in seconds, so let's put that in seconds as well. So that would be 130 seconds for 2 minutes and 10 seconds. The range of times, the median was 84. The upper quartile was 108. The interquartile range and the range are given, and we're not actually given the minimum and lower quartile. So the range is the difference between the maximum and minimum. So we're told that there is a 2-minute difference between the maximum and the minimum, so 120 seconds. So given that the maximum is 130, and the maximum obviously being the bigger one, we know that the minimum is 120 less, so it would be 10. And then the lower quartile, so we're given the interquartile range was 68 seconds. So the interquartile range is simply the difference between the quartiles. Given that the upper quartile is 108, and we're told the difference between them is 84, we need to do 108, take away 84. So that's going to be 16 plus 8, so 24. So now we have the 5 things we need to draw our box plot. So the height of this doesn't really matter too much as long as you're consistent, really. I'm going to do it in the middle, in this middle box here. So the first line, the minimum is at 10, so I go to 10 and I draw a line. I then go to the lower quartile at 24, so each big box is 20 and there's 10 little boxes, so each little box is worth 2. So I'm going to go to 2 boxes after 20, which is 24, and draw my next line with my lower quartile. My median is 84, so that's 2 boxes after 80, so it's here. And then the upper quartile is 108, so that's going to be 4 boxes after 100, which is here. And then the maximum is 130, which is in the dead center of 120 and 140. Okay, so to draw the box plot now, what we connect the middle 3. So the actual box is formed by our middle 3 values, and the 2 on the ends are the tails, or the whiskers if you prefer. So there we go, that's our completed box plot. So David was set a target. He had to complete the first half of his phone calls in less than 1 minute and 30 seconds for each. But how many seconds did he beat his target? So he had to complete half his phone calls. So the halfway mark is represented by the median. So the median was 84 seconds. So he had to complete half of his phone calls in less than 1 minute 30. So 84 seconds would be 1 minute 24. So let me write this here. So 1 minute 24 seconds. So his target is 1 minute 30. He did it in 1:24. So it's 6 seconds quicker. So on Monday, how many of David's phone calls lasted less than 108 seconds? So these questions will always be quite prevalent in truth. So it'll always be a value that you're given. It'll usually be the upper quartile, the lower quartile, or the median. In this case, the 108 seconds is the upper quartile. So the upper quartile is the 75% mark. So when it says how many of David's phone calls lasted less than 108, so 75% exactly took less than 108 seconds. So we need to just simply find 75% of 200. So 75% of 100 would be 75. So of 200, it would just be double it. So it's 150. So it's 150 phone calls. Cartons of soft drink are filled using an automated system. Each carton is a cuboid that has a base area of exactly 40 and a height of 13, correct to the nearest centimeter. Calculate the least possible volume. So the height is to the nearest centimeter. So the resolution is 1 centimeter. So for the error bounds, it's the resolution divided by 2 either side. So 1 divided by 2 is 0.5. So the highest it could possibly be is 13.5, and the lowest it could have possibly been is 12.5. When you think about it, it makes sense because it's rounded to the nearest centimeters. The lowest it could have been is 12.5. Highest it could have been is 13.5. Anyway, we want the least possible volume, so we want the height to be as small as possible. So we're going to go for this one here. So volume equals the cross-sectional area times by height. So we're going to use volume equals 40 exactly times by 12.5. So 40 times by 12.5, so 40 times by 10 is 400, and then 2.5 40s would be another 100, right? So that would be 500. Let's just double check this. So 40 times by 10, 400, and then 40 times by, 500. It's 500 centimeters cubed. Okay, the empty cartons moving on a conveyor belt pass under a filling gun that pours soft drink into cartons until they're full. Drink is poured into each carton at a rate of 8,000 centimeters cubed per minute, correct to the nearest 1,000 centimeters cubed per minute, okay? Calculate the greatest possible number of cartons that the automated filling system could fill in an hour. You can ignore the time taken to move from one full carton to the next. Right, so there's a reason that this is a part I. So this part I and part II means these are both part of the same part of question A, essentially. So what this means is we use this answer up here for this. And that's not really something you would know, but it's meant to be exam etiquette. So if you've done enough past papers, you should recognize things like this, or you should recognize sort of inbuilt hints in the exam. So it makes sense that the greatest possible number of cartons would use the least possible in the carton, because if it's filling less in each carton, it can fill more cartons quickly because it's putting less in there, essentially. So the empty cartons, drink is poured into each carton at a rate of 8,000 centimeters cubed per minute. Correct. Okay. So how many could it fill in an hour? So what we do is we assume the lowest, so 1 carton is 500 centimeters cubed. So the drink is poured at a rate of this, correct to the nearest 1,000 centimeters cubed per minute. So again, we need to create a boundary for this. So correct to the nearest 1,000 centimeters cubed. So it's 8,000. The resolution is 1,000, so it's 500 either side. So 8,500, 7,500. So we want the greatest possible. So we want the gun to be as fast as possible. So we're going to go with it can fill 8,500 centimeters cubed in a minute. Okay, so it'll do 8,500. So 8,500 centimeters cubed per minute. And each carton is 500, so it's going to be how many can it fill in a minute? That's what we're going to find, and then we're going to times it by 60. So it can fill this much in a minute, and each carton is 500. So 8,500 divided by 500. And again, you can bus stop this, but there's not really any great need to. How many 500s are in 8,000? So that'll be 2 per 1,000, so 16, and then an extra one on top. So that's 17 cartons per minute. And again, we've done plenty of bus stops here, so you can do this with the bus stop if you absolutely need to. It is an essential skill. If you cannot use the bus stop method well, you should not be taking this exam. So 17 cartons per minute, and then we want how many in an hour? So 60 times 17. So 60 times 10 is 600, and then 60 times 7, so 6 times 7 with a 0 on the end, that's 420. So 600, 420, so that is 1,040 cartons per hour. And let me just double check my calculation on this. So 17 times 60. So 60 times 10 being 600, 60 times 7 being 420. Yeah, so 60 times 10 is 600, 60 times 7, 420, so yeah, 1,040. Good. And I do believe there is a part B here, so I'll do this part B, and then we'll move on to this in the next video. So cartons of a different size are also filled using the same system. Each of these cartons has a square base, a height of exactly 20, and a volume of exactly 950 centimeters cubed. Calculate the length of the base of the square base. Okay, easy enough. So here is a diagram. So you're given that this B, and then this height is 20, and you're told the volume is 960 centimeters cubed. This is again another prism. It's volume equals cross-sectional area times height once again. So we find the cross-sectional area, and then because it's a square, we square root it. Really quite straightforward. So 960 is equal to cross-sectional area times by 20. So the cross-sectional area is equal to 960 divided by 20. So I will use the bus stop for this. So how many 20s in 9? None. How many 20s in 96? So we can get to 80, which would be 4 with 16 left over. How many 20s in 160? That would be 8. So it is 48 centimeters squared. So the cross-sectional area equals 48. Okay, so now we know that it's a square, so it's base times base. So b squared is equal to 48. So b equals square root of 48, and then we just use our surds here. So it says it wants it in the form of a surd, so we can do that quite comfortably. So splitting this is square root of 16, square root of 3. So square root of 16 is 4, and then root 3. So the idea of this is you split this into two numbers where one of them is a square number, so you know you can use the square root and simplify it. So your answer is 4 root 3 centimeters.